I'm Alexander Hefner, your host on The Open Mind. My guest today follows a team of elite scientists on a historic mission to take the first picture of a black hole, to help us answer deep questions about space, time, the origins of the universe, and the nature of reality. Scientific American editor Seth Fletcher is author of Einstein's Shadow, A Black Hole, A Band of Astronomers, and the Quest to See the Unseeable. He tracks the progress of assembling Event Horizon Telescope, a virtual radio observatory the size of the Earth. Over about 50 years, black hole studies have gone from obscurity to a thriving industry, noted Nature's Richard Panek reviewing Fletcher's compelling behind-the-scenes story. As reported in Science News last year, a single star careening around the monster black hole in the center of the Milky Way has provided astronomers with new proof that Einstein was right about gravity based on a confirmed measurement in the region near a supermassive black hole. Seth Fletcher joins me today to discuss these latest developments. And what is the latest, sir? Tell us.
The latest is that we're waiting for the Event Horizon Telescope to release the results from their 2017 observation, which was the first time they fired up the whole worldwide array to try to take a picture of the black hole at the center of the Milky Way. There's a lot to unpack there, so I'm sure we'll get into that, but
Sure.
We're hoping to see results soon.
Historically, for our viewers who are not familiar, what is the origin of the black hole? When did we first arrive at it intellectually as a concept?
Intellectually, it was right after Einstein published the first papers on general relativity, his theory of gravity. And a guy named Karl Schwarzschild, who was a German astronomer, he was on the Russian front in World War I, just doing math from the trenches, came up with this weird solution where it was a little like, dividing by zero is something familiar from everybody knows you can't divide by zero. It's a singularity, it's an undefined point. And for a long time the question was this just a mathematical curiosity or did it mean something physical? It took about half a century for people to accept that these singularities might actually exist up in the sky. It was the late 60s before people really kind of wrapped their minds around it. And John Wheeler, a physicist from Princeton, gave them the name black hole, which is what we call them today. Since then, people have come to terms with them, and yet no one has ever observed one. It's estimated that there are billions of them in our own galaxy, but they're still a total enigma.
How is it that we conceptualize something so definitively, or was it definitive, and yet it hasn't really been realized or viewed?
Mm-hmm.
In our minds, there's a way we can't access it.
Well, one thing to say is that astronomers have a lot of indirect evidence that these things are real. They'll find gas moving in a way that just can't be explained unless there's some really dense, basically invisible gravitating point pulling on it. There are lots of observations like this. They've accumulated over the decades. What has made it difficult for people to wrap their minds around black holes? Well, that's what took so long for people to accept that they might exist because they are so strange. The classical picture of a black hole, like the newspaper boilerplate definition, is a point in space which is so dense that gravitation is so strong that not even light can escape. And that's true, but they wear a lot of faces, and people are still coming to terms with them and how they're really made and what they mean.
How, as someone who edits science and writes and speaks with sources in the scientific community with great frequency, how do you compare this and the evolution of black hole theory to Darwin, for instance? When it comes to this question of substantiation, mm-hmm. and how much proof we can ascertain that with accuracy that something does exist or did exist?
That's a good question. Biology is not my strong suit, so I'm not going to try to compare it to the evolution of the acceptance of evolution. But what I can say is that what's so strange about black holes is that they are definitionally unobservable, in a sense. What these astronomers that I wrote about are trying to do is to get as close as you possibly can, which is to take a picture of its shadow. So,
Right.
so for something to be definitionally unseeable and to be a phenomenon that is actually made of warped space-time, pure gravity, kind of boggles the mind more than anything I can think of.
What motivates these scientists?
I think it varies from scientist to scientist, but for a lot of the astronomers, I think it's a technical achievement. It's just a really heroic, borderline impossible feat of engineering and perception. For some of the theorists who are involved, it's probably answering really deep questions about how black holes behave, how they interact with their host galaxies, how they eat. This is sort of a mystery. It's not easy for things to fall into a black hole. It's actually kind of hard. How they eat is like a really active subject of study. And then there's a really deeper level of theoretical questions that involve the collision of quantum theory and gravity that some theorists hope black holes might be able to help answer.
And how would they be able to help answer that question?
Well, it's unclear, but what we can say is that right now we have two theories of nature, roughly speaking. This is oversimplified, but we have general relativity, which is Einstein's theory of gravity, and that explains the universe on the largest scales. We also have quantum theory, which explains the smallest scales, the subatomic realm. Both are extraordinarily successful. Both are experimentally proven, to an incredible degree, but they also describe completely different visions of reality. And in a black hole, they intersect in a really interesting way. So Einstein's theory of gravity says that the interior of a black hole, inside the event horizon, which is the boundary, is a vacuum. And all the matter that went in is, in theory, crunched down into a point called the singularity, which is infinitely dense and infinitely small. And that doesn't make much sense because it just doesn't make much sense. There's something wrong with that picture. So there's something incomplete there. To figure out what really happens at the singularity, we have to know how gravity behaves when it becomes quantized. And you have to have a quantum theory of gravity. Well, some people say we don't have a quantum theory of gravity, but we actually have too many. We have trouble sorting through them. So people are really stumped on where to look for clues, where to go next. But taking a direct look at a black hole, where these things intersect so directly, is a really obvious and promising next step. Nobody really knows what they'll see, but it's possible that they could see something that proves that Einstein was absolutely right about general relativity and it doesn't need modified at all. Or it could be a little bit different than expected. And that would be a really fascinating clue to where this picture breaks down.
As we sit across from each other, the scientists are analyzing some data, I would presume, associated with the photographic evidence that they've compiled. What are they looking for?
Well, they've been trying to make images, and that process has been secret. The book came out while they were still in the process of analyzing the data from that observation. And what they do is they try to make pictures using the data. They try to make pictures that match the data. And then they try to falsify those pictures. They try to disprove them, and they try to debunk them from every angle so that they eventually arrive at something that they can all agree, yes, this is a depiction of something up there in the sky. And then it's a matter of interpretation. And there are lots of different ways to interpret this. I mean, there is just the question of, did they get a picture of the shadow of a black hole? If so, does it match the predictions of general relativity? But there are also a lot of subtler questions. They're looking at things like magnetic field strengths and lots of detail. So they're working through this on many different academic levels.
What are some of the broader applications, if any, of how physics can be taught, can be studied, and can be learned from your book and books that are yet to be written, the relevance of physics to our humanitarian existence?
So, I mean, there are a couple different ways I could take that question. One is that if tomorrow we have a working theory of quantum gravity, I don't think that it's clear at all how that would have technological applications. But, basic science is the foundation for all of technology. You just have to keep pushing, and then inevitably, applications pop out of these new theories. I mean, quantum mechanics is just totally bizarre, and nobody really totally understands what it means about the universe, but it's the basis for all of our electronics and computers, computing, communications, networks. So I would say that it's unclear, but in terms of humanitarian, when Einstein published his theory of relativity, and actually it's the 100th anniversary of this observation. It was right after World War I concluded. A British astronomer named Arthur Eddington set out to observe an eclipse and measure the bending of light from stars near the sun. And British scientists testing a German theory months after the conclusion of World War I, it was, in a sense, I mean, for some people, it was a sense to take down the new German theory, but for other people, Eddington was a Quaker and a pacifist. It was sort of like a reconciliation, and a lot of people have viewed that observation that way. I mean, not to get too kumbaya about the whole thing, but one thing that I find really interesting about these big international science projects is that they seem like one of the few places where people are still cooperating well on an international basis. Politics and nationalism and trade wars aside, scientists keep kind of plugging away on these projects that require international cooperation. And I don't want to make it sound like there's never any conflict between those scientists. I mean, they're humans, they're egos, and it's messy, but they generally get things done in a way that, we don't in other spheres.
The impact of AI and the internet and other technological innovations on human beings and their welfare. Are those things that physicists think about or not so much?
I think it's really hard to generalize, but and I don't know how to apply the sort of the lessons of this book to that. But what I do know is that the most active voices in, for example, regulating nuclear weapons have always been the physicists. Starting with Einstein and through, it's kind of ironic because a lot of actually the research that went into the development of the hydrogen bomb, for example, was actually used to prove that black holes are probably likely to exist in nature. And so some of the physicists who, there are physicists who directly contributed to the development of these weapons, but there are also physicists who have been extremely vocal and active about warning of their dangers and protecting them. That continues to this day, certainly.
What are the lessons of the book that you wanted to impart to our audience, especially for the next generation of scientists who might be interested in this pursuit of evidence of the shadow?
Yeah. I think, for me, it goes back to just being this incredible human accomplishment. No matter what they have seen, no matter what the results from the observation say, they managed to, unite radio observatories all around the world and observe with them simultaneously to try to take a picture of something that is definitionally unseeable at the center of the Milky Way. When I first started working on this project, one of the things that I really liked about it was that when you just say the facts of it plainly, it's about a group of astronomers who are trying to build an Earth-sized virtual telescope to take a picture of the black hole at the center of the Milky Way. Every little unit of that sentence sounds insane and impossible, but it's not. And so we don't know whether they got that picture, but they pulled off the experiment. They built the virtual Earth-sized telescope. And so, I mean, I guess the lesson there would be that these things take time, and they're work. They're grinding, grueling work that takes decades, and there's a lot of, in addition to the technical and scientific work, there's a lot of politicking.
What do they want to do next? And what were the obstacles to that achievement that they overcame, besides the linguistic barriers and being scientists around the country?
Well,
I mean, around the world.
I mean, to take what they want to do next, they want to keep taking more. They want to keep observing. You know, they've been, since the observation that, that they're hopefully going to be releasing results from soon, they did another observation. They've been upgrading the telescopes for higher frequencies and, more powerful digital processing and adding new telescopes. So they want to just keep seeing farther and farther and sharper and sharper. To go back to the obstacles, when they first realized that this could, in theory, be done, it was the late 90s, and they just simply didn't have the telescopes, but they were under construction. So it was, it was the late 90s when people started to realize that, in theory, with the right telescopes and with the right technology, they could do this. But the telescopes didn't exist and the technology didn't exist. But the telescopes were under construction. Big telescopes take a really long time to build, though. But eventually they came online in Chile, in Hawaii, in Mexico, and that unlocked a lot. The other thing that unlocked a lot was the development of what was the computing boom. And that enabled them to replace creaky reel-to-reel magnetic tape data recorders with solid-state hard drives, And now, so that sort of unlocked everything. And then, interestingly enough, what the majority of the drama that I observed while I was reporting the book was organizational, was human, was really about people trying to figure out how to form this intercontinental, worldwide group of people who would work together, and who gets credit, and which institutions get credit, and which people get credit, who has primacy, who does what. That was sort of the final obstacle. Once the engineering and the technology was done, that was the biggest obstacle.
How has the scientific process evolved since Einstein? If you want to start from that and his theory to the present and now testing the theory, would you say that the scientific process has been largely consistent? Of course, you're identifying novel technologies that, when implemented, enhance the capacity to see. But has the process changed at all?
Fundamentally, I would say no, in the sense of coming up with hypotheses and trying to discredit them with experiment and observation. I mean, that's the same. The tools have changed. Things are much more computation heavy now. Another thing that has changed, or is starting to change, and this is connected to the content of the book, though somewhat outside of the direct applicability, is that the fundamental theories of nature have gotten so hard to test that people have started, they're kind of desperate for evidence. They're desperate for things that could disprove the many, many theories that are out there. So, for example, they're looking to the sky. They're looking for, astronomical evidence. They want to build massive new particle colliders. But there's also this debate about, you will hear sometimes, and this is still a controversial idea, that maybe physical theories should be ranked by the probability of being correct instead of using falsification as the gold standard. And that's still really, really controversial, but that says something about how far into the realm of really abstract, weird theories fundamental physics has gone.
That's really interesting, that debate that you described. Where is it going? Who's winning it right now? I mean, the falsification model is still the consensus.
Right. Yeah, that's still the consensus. This has been going on for a couple decades now, but it continues to flare up. I mean, there there was a conference last year or the year before where some people were saying, like, maybe we need to look for new models for, judging fundamental physical theories other than whether we can build a particle collider that, disproves it or not. Because they've reached the realm where those things are so hard to build, they have to be so huge and so powerful that it's almost kind of hard to imagine them being built. And I don't want to oversimplify or overgeneralize here, but that's a debate that's happening right now. And I don't know who's winning. I would say that the conservative strain in physics is really strong, and most people still would like to find experimental or observational evidence to sort through these theories.
Right. Well, you mentioned from the outset that there are theories that physicists at least find hard to commingle or coexist. But what is the problem with having different baskets of theory? And that kind of speaks to, going back to the biology, our evolutionary strain, that there are always going to be a lot of different baskets of theories.
Well, there are people who say that's not a problem. There are people who say, well, what? We have the world looks one way at the subatomic level. The world looks a different way at the galactic and universe scale. So what?
Doesn't that make sense, or no?
I don't know, but a lot of people are, I have to be careful here because I don't want to. There's no universal opinion of the physicist, so I can't speak on behalf of.
No, understood.
But however, I will say that people are really dissatisfied, generally, with the idea that we have two different theories of nature, and they want to find a solution. That's just sort of the natural drive, and so that's part of what inspires experiments like this. Is you just go look for any place you might possibly find something that deviates from what we expect, that might give us a clue as to where one theory or the other breaks down, so that we can figure out how to pull this. I think about it as they're looking for threads to pull. It's like you have two sweaters and you want to knit it into one. You have to find the threads to pull that will pull them apart before you can stitch them back together.
And in the couple of minutes we have left, Seth, what about the future of science education? So how did this book inform the way you look at science education for a population that we want to be as literate as you are on this subject?
Well, I'm not a scientist, I should say that.
Science journalist.
Science journalist.
Yes. But you're an educator. You're a science educator.
Science education seems, it depends on the K through 12 situation. I'm not sure. I think it varies regionally. I know that I am incredibly impressed with all of the next generation of scientists, the grad students that I met, the grad students, undergrads working on the EHT. Based on watching them perform and talking to them, I'm not sure that there's really much of a problem with science education.
What can be the case for funding new theories, new physics, experimentation, that is going to be more than to stimulate our imagination?
Right. Well, we've long known that basic research is the engine of technological progress. So if you want to think of it in economic and technological terms, it's always been the case historically. So to shortchange basic research, whether it's into physics or whatever, astronomy or whatever, would be incredibly short-sighted. And
that's been the argument of NASA for some time, that they might find elements on Mars or some other planet that would be pivotal in curing a disease, finding a cure to a disease.
Right. I don't know, maybe I'm overly romantic about this stuff, but I think that we tend to do these things because they're kind of necessary. It's necessary to probe the frontiers of the, foundational knowledge. People have to do that. Whether the immediate applications are clear or not. And so, I hope we continue to do that.
And just for our viewers who are interested in, assuming this airs when the findings are available or are not available? Where should they go to find out what these astronomers saw or may see in the future?
Well, as soon as we have results, I'll be writing about them for Scientific American. So you can go to scientificamerican.com or Google the Event Horizon Telescope too.
And you talked about ownership of the data and propriety. Where is an educational resource? Is there some kind of consortium or some kind of collaborative where this data can be accessed at a major university or an educational website?
Not yet. I don't think so.
These are people, the folks who are viewing the potential hole or the shadow, who are in some cases affiliated with educational institutions.
Yes.
Most of them, right?
Yeah. I would say right now the data is not publicly accessible because they are doing their proprietary analysis of it. But what the ultimate fate of the data is a good question, because they do come from big publicly funded observatories. So I would imagine things will open up eventually.
Thank you, Seth.
Thank you.
And thanks to you in the audience. I hope you join us again next time for a thoughtful excursion into the world of ideas. Until then, keep an open mind. Please visit the Open Mind website at 13.org/openmind to view this program online or to access over 1,500 other interviews. And do check us out on Twitter and Facebook at OpenMindTV for updates on future programming.
Continuing production of The Open Mind has been made possible by grants from Ann Olnick, Joan Gans Cooney, Lawrence B. Benenson, the Engelson Family Foundation, Alfred P. Sloan Foundation, the John S. and James L. Knight Foundation, William and Flora Hewlett Foundation, Joanne and Kenneth Wellner Foundation, and from the corporate community, Mutual of America.